Okay, so thus far we've talked about uh, electric charge, uh, charging objects, transferring charge. Um, we've mentioned conductors and insulators. So what we're going to talk about now is the force associated with charge. So this is governed by something called Coulomb's law. And this is in section 5 of chapter 21. So Coulomb's law, um, suppose we have a couple charges here, and usually use the letter Q to indicate charges. So, and actually, let's see, I have them the other way around in my picture here. Q2 and Q1. Uh, so the and we have these separated by some distance r, let's say. The force between these two charges is going to be given by the following. This is Coulomb's law. So it's going to be proportional, so this is a constant, times the product of the two charges divided by the square of the distance between them. So this form should hopefully look kind of familiar. This is an inverse square law. Because it's inversely proportional to the square of the distance between them. It's really identical mathematically to gravity. So hopefully when you see this, you're like, ah, this looks kind of like Newton's law of gravity. So if you recall, remember back from the first semester physics, the force associated with gravity. So let me actually, I'll put this as electric force. The gravitational force was big G times the product of the masses divided by the square of the distance between them. But there's one important difference. So unlike charges, which can be positive and negative, mass is always positive. There's no such thing as negative mass. Which would be pretty wild, actually. That would correspond to, objects pushing each other away, which would be really strange compared to our conception of how gravity works, right? Negative gravity. So a couple other details to mention about Coulomb's law. So for gravity, we talked about big G as being the constant. Well, for the electric force, this K is really sort of shorthand for the following. It's 1 over 4 pi epsilon naught, where this epsilon naught is really the fundamental constant. It's called the permittivity of free space. And it's associated, it's related to the speed of light. We'll get into that later, but this number is equal to 8.85 times 10 to the minus 12 coulombs squared per Newton times meter squared. So you can see the units of that are such that when you multiply by, or let's see, when you have a factor of charge squared, and you divide by charge squared, and over r squared and multiply times m squared, you end up with newtons, which is what we want because we're talking about a force. So there's that. And then the other thing that I wanted to mention and be a little more rigorous about is just that this is a force. So this has direction. It's a vector. So this, what I have written so far is just the magnitude. This is just, kind of the size. And that's good enough for dealing with a lot of problems. And that was often how we dealt with gravity problems. But recognize it's a little more complicated now because since we have positive and negative charges, we have to be a little more careful about keeping track of the directions of things. So let me give you really the more complete vector definition of this. So let me just be a little more detail-oriented here. Really, this R, we know that this force is going to be directed along a line between the two charges. And so let's call that would be the vector between them. So I'll use my arrow over the top to indicate vector. And there would also be a unit vector associated with that, right? That would point between these. That would it would have a length of 1, right, as a unit vector, and it would just contain the direction information. So we would call that R21 hat. My drawing is a little bit muddled. So like that, R21 hat. So really the better and more complete way of writing this would be to say, okay, the force. Now, another note or thing to be careful about with this is to be very mindful of your subscripts. So we're going to call this 1, 2 for the force on 1 due to 2. I would encourage you to just be very explicit about this until you get comfortable with it. So that would be a vector. The magnitude of that we already talked about, so that will be K Q1 Q2 over R21 squared. And then the direction would be given by that unit vector, R hat 21. Now, sorry, I erased my unit vector here. So notice that we're talking about the force on charge 1 due to 2. And if both of these charges are positive or both of them are negative, that is going to point away. So it'd be pointing like that. However, if one of them was positive and one of them was negative, then it would point the other direction. Like that. Okay, so, and then, we could talk equivalently about the force on 2 due to 1. Notice all the quantities, the charges are the same, the distance is the same. But now the unit vector that would describe that would be R12. R12 points the other direction. R12 hat. So that's just the more complete vector definition for Coulomb's law. Okay. Anything else I wanted to mention about Coulomb's law? I think we should look now at an example question. You'll get comfortable and more familiar with. Oh, one other thing I would mention with regards to uh, charges and Coulomb's law is that we've just talked about two so far, but if you have multiple charges, the force is going to obey superposition. So what you can do is you can just add up the forces due to those other charges to find the net force. You may or may not have seen gravity questions like that if you had more than two masses to find the net force of gravity on some mass. I'll show you an example right now to hopefully sort of emphasize that fact. So let's look at an example question. Okay, so let me show you an example here. Let me paste in a question. Okay, so this question, we have three particles of charge 75, 48, and negative 85 microcoulombs placed in a line where the center particle is 0.35 meters from each of the side ones. And we want to calculate the net force on each charge due to the other two. So this is a application of Coulomb's law. So before we find the net force, let's just calculate the force between two of them, just to do sort of the simple case to get ourselves started, and then we'll do the more complicated situation. So before we get going here, let's label some of this stuff so it's just a little bit easier. Let's call this Q1, this Q2, this Q3. Let's recognize that the distance between these is 0.35 meters. And so for our first objective here, let's just find the force on 1 due to 2. So I'll just put down here on 1 due to 2. And that's going to be K Q1 Q2 over R squared. And the direction information for this, so if we're looking at the force on 1 due to 2, that would also have the unit vector R21. Okay. And recognize since these charges are both positive, that would be pointing like this. Okay. Because of course R21 would be like that, R21 hat. Okay. So what are our values for this? Let's 1 over 4 pi epsilon naught times 75 microcoulombs times 48 microcoulombs all over 0.35 squared. If we crunch the numbers there, we would find that this is negative 264, let's call it negative 260 newtons. And notice this unit vector R21, let's put this in a little more common or a little more familiar notation, if this is, this problem is limited to one dimension along, we could say it's along the x-axis, in which case, if that's pointing along the negative x-axis, this would be in the I hat direction, or the negative I hat direction, as I have it there. Okay, so that's the force on 1 due to 2. What else? Let's look at now the force on 1 net. So that's going to be the force on 1 due to 2 that we already calculated, as well as adding vectorially to that the force on 1 due to 3. So let me just, I just want to emphasize, be cautious with your subscripts. So I'm just going to explicitly say what these are for now. And hopefully this will kind of help as you get more comfortable and familiar with this. And then, you will want to establish your own habits for this, but I'll just put on 1 net is going to be on 1 due to 2 plus on 1 due to 3. So what does that actually look like? Well, this will be the same. This piece is the same above, plus the additional piece. Now, notice this one, while force 1, 2 was in the negative I hat direction, since these charges are opposite, this is actually going to be positive. That force is going to point in the other direction. So something like this. So, and there's different ways that we can represent that. We could think of that as a negative R 3, 1 hat. Or I think it's, with a one-dimensional problem like this, it's just more straightforward to think in I hat. And so that would be a positive I hat contribution. So let's see here. We would have 75 microcoulombs, 85 microcoulombs. Now this is, instead of 0.35, we're going to have 2R, so this would be 0.7 squared. And notice I have this one. This would be positive. It's in the positive x I hat direction. And we find when we compute this, we get negative 147, negative, let's call it negative 150 newtons in the I hat direction. So this is a way of saying that this F13 was not as large as F12, but it was positive. You can see it sort of canceled out some of the negative F12. Okay, so let's look at another one here. How about F1, or sorry, not F1, F2 net. So call this on F on 2 net. What's that going to equal? Well, that will be the force on 2 due to 1 plus the force on 2 due to 3. So I won't put these little notes here under the subscripts. I just wanted to be kind of very explicit with it initially, and then to get you started. And then as we go forward, we'll get a little more sparse with our notation. So what is this going to look like? Well, We'll have K Q2 Q1 over R squared. Now let's think about the directions here. This, the force on 2 due to 1, that is going to be a repulsive force. So it would want to push Q2 in the positive I hat direction. And then the force of 3 on 2 is going to be K Q2 Q3. And now in the distance in this case would just be our regular R. So let's run the numbers here. So this will be 1. Oh, and I should say that one is attractive, but that negative, that Q3 is to the right of it, so it's also going to be a positive I hat contribution. I think it can be useful for straightening this out to here. Let's just make a little cartoon. So if this is Q2, we can see that F1 on 2 would be pointing to the right. It's pushing it away. But F3 on 2 would also be to the right because it's attracting it to the right. So this can be a useful, if in doubt, draw yourself a little picture to help keep track of directions. And let's put in our numbers here and calculate this. We could actually, 2 da, da, da. And we find when we compute these, plug in our numbers and calculate this, we get 560 newtons in the I hat direction. And we could do, the same sort of procedure for the force on 3 net, but I think we've kind of gotten what we can from this question. I think hopefully this kind of that would be sort of the same type of procedure. We can add the forces due to the 2 charges, so 1 on 3 and 2 on 3. And find the net force, and of course being mindful of the directions, etc. So hopefully this kind of gives you a sense of the procedure for finding using Coulomb's law, as well as how you can use the superposition principle to find the net force on a charge due to multiple other charges.